Hello everyone, welcome back to the channel. Today we are doing Leetcode 3201, find the maximum length of valid subsequence 1. So let's have a look at what the problem statement says. It says you're given an integer array nums, okay. Now what we need to do is we need to return the length of the longest valid subsequence of nums. Now what does a valid subsequence mean? A subsequence sub of nums with length x, a particular length, is called valid when it satisfies this particular condition, and this particular condition says that okay, sub of 0 yani subsequence sub and sub of 0 plus sub of 1, so the sum of the first two terms mod 2 should be equal to the sum of the second two terms mod 2, and so on and so forth. So each and every subsequent pair, their parity should be equal. So I can say, okay, we are focusing on parity of pair sums, isn't it? Now, we'll better be able to understand this when we look at the test cases. So for example, in this test case, the sum of the first, the sum of the first pair is actually 3, then this is 5, then this is 7. And since we're talking about parity, you can very clearly see that all of them are odd, isn't it? So if I sort of calculate their parity, it's going to be 1, 1 and 1. So it's all equal throughout. Therefore, the answer to this particular test case is 4, meaning that this whole particular array as a subsequence is the longest valid subsequence. Okay, now this test case is actually very interesting, and this leads to this leads to much insight into what the question actually wants us to do. Now let's say that I calculate the sum of all of these pairs. Okay, so this is 3, then this is 3, then this is 2, then this is 3, this is 3, and then this is 3. Now, if you think about it, I am most interested in the parity of the sums, right? So, okay, let's see. If I take this one and this one, so the sum that I currently have is 3. Now, I can take this one also because the sum of 2 and 1 is 3 and the parity is the same. But I shouldn't take this one. Why? Because 1 plus 1 is equals to 2, right? And it's going to sort of break my streak. So I'm going to ignore this. Okay, so what I'm really essentially saying is I am going to take some numbers and I'm going to not take some numbers. I hope this rings a bell, right? I'm going to take some numbers and I'm going to not take some numbers. Right. So okay, then again, since the parity is 1, 1 and 1 over here, and 1 plus 2 is also 3, as a matter of fact, I'm lucky in this one that 1 plus 2 is also equals to 3, so I'm going to take this one, and this one, right? But if you think about it, there could have been a scenario where there was an even number over here. So for example, after ignoring this, even though the sum over here is 3, but this sum actually represents this 1 plus 2, isn't it? It was my luck actually that this 1 plus this 2 is also equals to 3, and this leads to a odd parity. But essentially what I'm doing is I'm ignoring this particular one, right? So what we are doing is basically, if we ignore this particular one and we take the rest of the elements 1 2 1 2 1 2, then we get the answer of this particular test case as 6. So maybe it tells me, okay, not do not think about in terms of sum, think about in terms of what the actual numbers are. Because you see, if you're ignoring this particular one, then this particular sum is no longer valid for you. Are you getting my point? It was my luck in this scenario that this was also a 1, but it couldn't have been. For example, let me change it for you. For example, if the scenario was 2 1 2, okay, so this is 3, this is 3, and this 2 plus 1 would be equals to 3. This would be a different test case, but chalo, we'll dive more into this later. But for now, let's keep things simple, right? This actually changes the test case. In this scenario, the answer would be 7. Why? Because 2 1 3 1 2 3 2 1 3 1 2 3, and then so on and so forth. So, and actually, chalo, interesting thing about this is that what you're observing is actually a pretty interesting thing over here. Now what you'll be observing is this number is even, this is odd, this is even, this is odd, this is even, this is odd, and this is even as well. So one might think at this point that okay, if you have alternating, if you have alternating parity, it gives you a good enough answer, right? If you have alternating parity, So you have a good enough answer, and why don't I just sort of find out the pattern, find out the subsequence which has the longest alternating parity. Like in this scenario also you have alternating parity, odd, even, odd and even, right? So one might think of that, okay, this problem can be transformed, and this can be sort of be thought of in a way that I only need to find the longest subsequence which have alternating parity. But then if you think about this test case, both of them are odd. But the answer to this test case is obviously 2. And now, I'll give you an even better example. So for example, if I extend this one, 5, 7, let's say, this is odd as well, this is odd as well. But if you think about it, the answer of this test case is going to be 4. Why? Let's think. 1 plus 3 is 4. Okay, 3 plus 5 is 8. And then 5 plus 7 is what? 12. And all of them, mod 2 is equals to 0. You see, so equals and equals. This is not alternating parity. This is the same parity, isn't it? So what we are getting to know from this particular test case and this particular test case is that, okay, if we think about the brute force, what I can do is I can just simply generate all the subsequences, and then we'll check which of them are valid and which of them are not. But then what can we extract from this particular test case and this particular test case, which is going to help us optimize, right? Now think about it a little, pause the video for a moment and think about it a little, right? Okay, so let's say that this is the test case that has been given to me, right? Now I'm obviously not thinking in terms of the brute force approach, because I know for a fact, given that the constraints of the problems are 2 into 10 to the power 5, it's obviously not going to pass, right? So let's see what I can do differently. Now if I start to think, what could be all the possible scenarios, right? What are all the possible scenarios? Let's see. Now we are talking about, either it's going to be the case of alternative parity, right? Or if it can be the same parity as well. You see, why am I saying so? Because one test case is one that says 1 2 3 4 5, so the answer is of this is also going to be 5. Why? Because if you take all of them, then 1 plus 2 is what? 3. 2 plus 3 is 5, 3 plus 4 is 7, and 4 plus 5 is 9. So you see, an odd number and an even number makes another odd number. Odd, even odd makes an odd number. Odd even makes an odd number, so on and so forth. But for example, if all of these numbers were like 2, 4, 6, 8, 10, then even plus even makes an even number, right? And all of them are even. So the parity is going to be the same throughout. The answer of this particular test case is also going to be equals to 5. And for example, if you had something like 3, 5, 7, 9, then 3 plus 5 is 8, 5 plus 7 is 12, 7 plus 9 is 16. Odd plus odd, if you combine two odd numbers, they also make an even. So what I can extract from this is that if the parity is different, if the parity is different, then the sum which you are getting is even. And if the parity is same of two numbers, wait a second. For example, if I have different numbers like 2 plus 3, if I have different parity, sorry, if I have different parity, 2 plus 3, it gives me an odd number, I'm sorry. But if the parity is same, then you get an even number, right? So for example, if it's 3 plus 3 or if it's 4 plus 4, in both the scenarios you're going to get an even number, right? So all the possible scenarios are, I could either have alternating parity in my nums, or I could have the same parity throughout my nums array, right? So alternative parity means that you are either going to start with, you know, even, odd, even, odd, or you're either going to start with odd, even, isn't it? Now let me actually tell you what that actually means. Let's say we are talking about alternative parity right now. Okay, so this is odd, this is even, then this is odd. This is odd as well, so I'm going to ignore it for now. I'm going to ignore it. Then this is even, this is odd, and this is even. So since this is an alternative parity of this particular case, it gives me an answer of how much? It gives me an answer of 6. Okay, I'm going to keep track of which strategy is giving me what answer. Perfect. Let's try the other strategy, which is that I start with an even number, right? Because there could be possibly a scenario that If I start with an even number, it might give me a better answer. So for example, this is the first even number that I have, even, then odd, then even, then odd, then even. Okay, so this particular strategy is giving me an answer of 5, which is sort of not better than 6. Now what are the other two strategies that I have? I have the strategy of same parity, so even throughout, or odd throughout. So let's see what answers do these strategies give to me. So for example, if I'm doing even, 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 then I'm going to take this and this, so I'm going to get an answer of equals to 3. And for example, if I'm doing odd, odd, odd throughout, then I'm going to get an answer of 4, as you can very clearly see. And in amongst all of these cases, the best answer is 6, so we return that. No matter how hard you think, you cannot think of a pattern other than these what I've written in front of you. So there are two strategies, there are two patterns which belong to the alternative parity, and there are two methods which belong to the same parity, and that's it. This is basically what enables us to optimize our approach and think of a better solution than O of 2 to the power n. Because just like I said, if I was thinking in terms of take and not take, then I would have to have generated all the subsequences, and that's clearly an O of 2 to the power n operation. But if you think about it, now since we have reduced the problem to just 4 scenarios, every single scenario can very easily be checked in O of n. So I'm just doing 4 times O of n, right? So let's see how this can be implemented into a very distinct approach, and then let's see how we can code this up. Right, so what I can do is, since I know that there are only 4 patterns that exist, I can have a for loop for each of the patterns. So first of all, I can have a for loop which starts with an even number. It sees an even number over here. Then for example, let's say I have a looking for variable, right? Looking for variable right now stores an alphabet. It could be a number as well, it could be an alphabet as well, it doesn't really matter. But what essentially I'm saying is that I'm looking for an even number. I see that even number over here. As soon as I see that, I'm going to change this to what? I'm going to change this to odd. Now I'm looking for odd I get over here, right? And similarly, I'll be sort of maintaining a count, and I will say, okay, since I have an even number over here, I'm going to increment my count. Then I have an odd number over here, I'm going to increment my count again. Similarly, right now I'm looking for an even number. This is not an even number, right? But this is, so even, odd, and then even. So the answer which I'm going to ultimately get is 5. Similarly, for odd, I'm going to start by saying that, okay, the count is initially 0 and I'm looking for an odd number. I see that odd number over here, I increment my count. Even over here, I increment my count. Then odd over here, I increment my count. Even over here, odd over here, even over here. Ultimately, the answer which I get is 6. So this count is basically temporary, and overall, I'll be seeing that what's the maximum answer that I am able to achieve up and until this point. So I could have 4 for loops and very easily accomplish this, right? But let me actually tell you what is a more efficient way of writing this code. Rather than having 4 different for loops, you could have one nested for loop, and you could just do this thing inside of a single for loop, right? So let me tell you how this works. So what I'm going to do is, see, I have created a vector of int patterns where 0 indicates basically that you have an even number, and 1 indicates that you have an odd number. So I have 4 different parities over here: even, odd even, and odd, right? I'm going to iterate over each pattern, and I'm going to do the very same thing that I did over here, but rather than having 4 for loops, I'm going to have just a single one. I'm going to say that, okay, for each pattern, what you have to do is you have to traverse over the nums array, and what you have to do is you have to see that if the current number, so if the parity of the current number is equal to the parity of the pattern over here, all right, is equal to the parity of the pattern over here. And how I'm going to establish that is by saying pattern of count mod 2, and this is actually a very beautiful strategy. If it's so for example, if I have gotten an even number, if it matches this, I'm going to say, okay, count plus plus. Now you see, why have I done count mod 2 over here is because let's say that I'm looking for an even number, I get an even number, I increment my count, right? Count becomes equals to 1. then I'm going to again see an even number and I'm going to match it with this particular 0. Then when I increment my count, when count becomes equals to it's 0, then it becomes 1, and then it becomes 2. So 2 mod 2 is going to be 0. So the next comparison that happens between I mod 2 is going to be with this one. It 2 mod 2 is 0, right? Similarly, what you can do is, for example, if I mod 2 right now is even, it's going to get compared with this one. Then you're going to be seeing pattern of count will be equals to 1. So you're essentially you're looking for an odd number, then again you're looking for an even, then you're looking for an odd. So this count mod 2, basically what it does is it achieves that sense of repetition. So you first compare I mod 2, the parity of the current number. Let me actually write down a comment over here as well. Parity of current number. First of all, you compare the parity of the current number with this particular value, and then you compare it with this particular value, and this pattern goes on and on for the whole of nums, right? As simple as that, nothing too complicated. And in each and every iteration, what you're going to do is you're just going to keep track of whatever your maximum answer is, and if the count is greater than that, right? So in each pattern, inside 4 times basically, the count is going to be initialized as 0. So let's see if it passes all our test cases, right? It clearly does. Let's see if it passes all the other test cases that we have. Perfect, right? And now if we look at the time and space complexity, we already know that the time complexity is very clearly O of n, right? And the space complexity, if we observe, we have taken a constant space in order to store the patterns, right? It does not depend any, like it has no relationship with what the input size is. And other than that, we are just taking this count variable, and that's it. So the space complexity is O of 1. We are taking constant space, right? So yeah, I hope you found the video helpful, and I will see you in the next one.